transform and parabolic equations and Fourier series. And pick, important topics from there. Again, does anyone not want to meet next week? Is there anyone who can't? If someone is willing to take next week, that would be wonderful. If not, I could.
I already volunteered last night.
Okay, so do you want to continue this kind of stuff and just do briefly operator things?
Yeah, I can do that.
Okay. And then next semester, I'll send out an email. Hopefully I have everyone's email, and we can discuss what day of the week we want to meet that question again. And then start with Fourier series, the Fourier transform, parabolic equations in that chapter. Does that sound like a good idea?
Let me say a couple of words about this Fourier transform and some of the relations to the operators. That's what we talked about. Well, why do you care about function analysis and operators in PDEs? Well, if you look at linear equations, then you basically looking at something like this, where L is a differential operator, U is unknown. This is given, right? And this is unknown. And this one is a, say, partial differential operator. So, well, in some domain, and then you could impose some boundary conditions, whatever, but basically you want to solve it. So given F, find U, right? So how would you do it? Well, provided everything is nice, what you would do, here's the solution. So what do you want? You want to find an inverse of that operator, which we call green function, or resolvent, or whatever. So that's why you care about these operators. You need to find the inverse. Well, if this operator is not partial differential operator, but say the integral operator, you look at equations that usually they look a little bit different, but if they are linear, it will still be of the same sort, and then you would need to find its inverse. Okay, so that's what we do. Some of these operators, well, let me give you another example. Well, let's say you have a heat equation. Well, heat equation, diffusion equation, Brownian motion, whatever, they all look like this. You have something like dt of u is equal to L, or ul is some operator. Well, it has to be elliptic, but it doesn't matter now. Just imagine it's some operator, and t is time, and this acts in some other variables, like space variables, and you would have a u of 0. Well, it's equal to something, but that's where x is space variable. So you have an initial, say, heat distribution, and you want to find it at a later time. You need to solve this problem. Well, how would you do it? Well, let me put plus equal to 0. Just change sign of it. Well, again, it's not that difficult to solve it. It's basically, well, usually you would write it like that. The solution is u of tx is basically u of negative tx. That's x. Well, that's the initial value, because when t is equal to 0, you get this, right? And then when t is not equal to 0, you need to understand what this is. That's an exponential of a differential operator, right? And so what is it? Well, you can define it. It's not a big deal. I could give you examples how to define it. But that's why you need to know how to deal with these things. Well, that's called green function. That's called heat kernel of the operator L. You know, they are related. If you know this, you will know that, and vice versa. Well, I mean, depending on that operator, you may or may not be able to compute this exactly, but I mean, in simple situations, it's not that difficult to guess it. Well, let me give you one particular example. Let's say, well, suppose that L is just negative dx squared. Just in one dimension, for example. I could do it in n dimensions, but just for the sake of example. So you have that, and your domain is the whole real line. So, and how would you solve this? Well, you would, because it's these, well, it has constant coefficients, then the right thing to do is to expand this function in Fourier series. So you would say f of x is dp of 2d I px as t. So that's the Fourier transform of the function f, and then you would add e of minus tl on f of x is e of t d squared acting on this, right? Well, of course the integral is what we call R. Doesn't help you much until you realize that the derivative acts on these plane waves in a trivial way. So this is just equal to, well, this is derivative with respect to x, remember? So it is ip e of ipx, right? Which means that this derivative to the power n is ip to the power n, right? And so if you want, you could take it to the power 2n, then it will be 2n.
That's like known as f hat of p.
What?
F hat of p.
Yeah.
Right?
Yes. And then if I divide it by n factorial, then this is divided by n factorial multiplied by t to the n. Well, and then you can sum from 0 to n. You notice that this is nothing but e of t d squared, and just expansion of this exponential. And of course, this is, well, if you sum over n, that is e of negative tp squared. So in other words, e of t d squared acting on this Fourier exponential is just e of negative tp squared plus p. So you know how this acts. That's the point of doing Fourier. I mean, you don't know how this acts on the function is. Once you've done Fourier, you only have to act on this, and that's easy. That gives you this. So then you substitute it here. You get e of 2 pi e of minus t p squared plus dx. And you could leave it there and say, okay, here is my final result. Here is my solution. But of course, it's nicer to express it in terms of the original function f. And so you could then say, well, let's express it back by doing Fourier. So f of p of, that's the inverse of that. This is equal to dx e of negative I p, well, now there are two letters, we call it y, I p y, f of x. Well, this integral of that is equal to this f hat of p. That's the inverse of this Fourier. Okay? And what remains is the integral of a p, e of minus t squared plus I px. Well, actually, the integral of a p, well, this should be brought inside, so it's minus I p1. Well, and that integral is easy to compute. It's a standard Gaussian integral. Gaussian integral is an integral when you integrate over the whole real line of something that is exponential of a quadratic polynomial, like this one, in any dimensions, times any polynomial. Well, here the polynomial is just one. and well, this integral is equal to 4 pi t negative 1/2 e minus x minus y squared over 4t. Well, if you ask myself, how do I know this? Well, I do this probably 100 times every day for the last 30 years of my life, so probably I know that pretty well. So that gives you this formula. Well, and this expression, and those of you who took PDE before, you've probably seen it. This is called the heat kernel. That is the integral kernel of that operator. That's the, if you want heat operator, it's called heat semigroup. And that's its integral kernel.